So in 46, we've got a function f of x is sum from n equals 1 to infinity of negative 1 to the n plus 1 times x minus 5 to the n over n times 5 to the n. So let's determine the interval of convergence for this one. And to do that, we're going to do the ratio test again. That's kind of standard for us for a lot of these. A sub n plus 1 is going to be negative 1. N plus 1 is going to be n plus 2. X minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1. This term right here is our a sub n. So let's form the limit as n approaches infinity of a sub n plus 1 over a sub n. As usual, I'm going to ignore the negatives because they're going to cancel each other out for the most part, and then you're also taking the absolute value. So it's just the limit as n approaches infinity of a sub n plus 1, at least the part other than negative 1 to the n plus 2, x minus 5 to the n plus 1 over n plus 1 times 5 to the n plus 1. Divided by this is the same thing as multiplying by the reciprocal. So the reciprocal is going to put the n times 5 to the n in the numerator and x minus 5 to the n power in the denominator. Like that. We're going to get a lot of nice cancellation here. Let's do that. Let's start by knocking out n of these. Now you can take a look at the difference here. We've got n plus 1, and then here you've got n. So you're going to leave all but one of them. One of them is going to be left in the numerator, and that's it. In a similar fashion, you've got n of them here and n plus 1 down here. So all of those cancel, leaving you with 1 in the denominator. That is 5 to the first power, or just 5. So let's clean that up a little bit. That's going to be the limit as n approaches infinity of x minus 5 over 5 times n over n plus 1. Now I split it up like this because this part right here doesn't depend on your limit. So effectively it's a constant. And I can factor that out in front. That's going to be the absolute value of x minus 5 over 5 times the limit as n approaches infinity of n over n plus 1. What's that limit? A couple of you said it. Not 0. It's 1. This whole thing turns into a 1. So overall, that's going to be the absolute value of x minus 5 over 5 for the limit. In order for this to converge, by the ratio test, we need that limit is less than 1. So x minus 5 over 5 is less than 1. Now because I'm dividing here, I can split that up as x minus 5 in absolute value over the absolute value of 5, which is just 5. Or in other words, so from here to here, or equivalently, absolute value of x minus 5 is less than 5. So at this point, it's telling us that our radius of convergence is 5, but that doesn't quite give us the interval of convergence. So the interval of convergence is going to look like this. X minus 5 is less than 5 and greater than negative 5. Adding 5 to all parts of this inequality, I get 0 is less than x is less than 10. And that's your interval of convergence. Now we're not quite done here. What else do we have to do with respect to 46 here? Yeah, you got to test the endpoints. So at x equals 0, got to go all the way back to the original series. You'll have 0 minus 5. We'll have negative 5 to the n. So let me put that in here. It's going to be the sum from n equals 1 to infinity of negative 1 to the n plus 1, negative 5 to the n over n times 5 to the n. We've seen stuff like this before. Negative 5 to the n is going to split up as negative 1 to the n times 5 to the n. And I'll get a little cancellation down here. Let me show those steps. N equals 1 to infinity, negative 1 to the n plus 1, negative 1 to the n times 5 to the n. So I'm splitting this up into two terms. And the nice thing about that is that allows me to cancel out 5 to the n. This gives me negative 1 to infinity of negative 1 to the 2n plus 1 over n. Okay, well that's good. But what does this series do? Does it converge or diverge? Diverges. Essentially, negative 2 to the n plus 1, I think I still have that on my calculator. If you, no, I'll see. If you look at, no, I can't do it that way, sorry. If you look at negative 2 to the 2n plus 1, this is always going to be an odd exponent. So effectively this is n equals 1 to infinity of negative 1 over n. It's just the negative of the harmonic series, or a p series with p equal 1. However you want to look at it, it diverges. All right, let's take a look at what happens at the other endpoint, at x equal 10. So at x equal 10, I think our simplification is going to be a little bit easier. Putting in the x equal 10 here, 10 minus 5 is going to be 5. So we'll end up with the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 5 to the n plus 1, or no, just 5 to the n, sorry, not 5 to the n plus 1, over n times 5 to the n. These terms cancel each other out. Yay! So that's pretty nice. You're just left with the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n. What does our work on convergence or divergence of series tell us about this? Converges by the AST. It's an alternating series. It decreases towards 0 monotonically, so great. It converges. The bottom line is it converges. So your interval of convergence then is 0 is less than x is less than or equal to 10. So that's where this actually works. It turns into a function on that interval. Let's play with this. There's some interesting and amazing things you can do with these series, especially on their interval of convergence. For starters, let's find the derivative of f with respect to x. So we're going to go back here. This is really part B. We're going to find f prime of x. Let me remind you real quickly here that f of x, let's see where do I want to write it. F of x itself, the original series, was negative 1 to the n plus 1. Well, I should put the sum, n equals 1 to infinity, negative 1 to the n plus 1 times x minus 5 to the n over n times 5 to the n. That's our original series. What's going to happen when we differentiate it? Well, it's not really stated explicitly, but kind of implicitly. We're differentiating with respect to x. So the only term that really matters when you differentiate with respect to x is going to be this one. Everything else is a constant, and you're adding all these terms up. Remember, that's what a series is. It's the sum of all these terms. So let's just differentiate d by dx of x minus 5 to the n. What would that give me? N times x minus 5 to the n minus 1. Okay. Let's put that in here. So f prime of x is going to be the sum from n equals 1 to infinity of negative 1 to the n plus 1 times n times x minus 5 to the n minus 1 over n times 5 to the n. I hope you don't leave it like this. Why not? There's a little something you can do to simplify this. Cancel the n's, right? Let's get rid of the n's. So we're left with the sum from n equals 1 to infinity of negative 1 to the n plus 1, x minus 5 to the n minus 1, over 5 to the n. We don't have time to go through all of this, but let me just share with you this much. The interval of convergence, at least initially, starts out at 0 to 10. Now what's interesting about that? It's the same thing as f, right? You still have to check the endpoints. Now, what's odd is that for the derivative or the integral, the interval of convergence can change at the endpoints. So I could lose the 10 and pick up the 0, or I could get both of these. It's just going to depend on the particular problem. You still have to check it through. And in this particular case, I think this is what it ends up being. I don't think you get any more convergence. So it's just going to be 0 to 10 would be your interval of convergence. That is, it doesn't check on either endpoint. But great, so you're able to differentiate these things and integrate these things term by term. And that's going to have some nice implications for us in section 9.9. Let's go the other direction. Part C. Let's find the integral of f of x dx, which is going to be the integral of the sum from n equals 1 to infinity of negative 1 to the n plus 1 times x minus 5 to the n all over n times 5 to the n. Oh, you should be hollering at me. What did I forget? dx, thank you. We're integrating this with respect to x. So that's important to realize that you're integrating with respect to x, because everything that's not an x can come out of the integral. So this is the sum from n equals 1 to infinity of negative 1 to the n plus 1 over n times 5 to the n times the integral of x minus 5 to the n dx. So basically, I can ignore all this stuff. I just have to integrate that last term. Now, I'm hoping that we don't have to actually do a u substitution to do this. What's going to be the integral or the antiderivative of this term? Add one to the exponent, divide by the same exponent. So I think somebody's said it right. x minus 5 to the n plus 1 over n plus 1. The interval of convergence gets inherited. It's going to be 0 to 10, just like it was for the derivative and just like it was for the original function. You still have to go through and test the endpoints. I'll leave it up to you. Do you want to test the endpoints? Do you want me to just tell you the happy ending? It's whatever you need. Happy ending? Okay. All right. Happy ending is that it tests out at both endpoints. So the interval of convergence is this. So a little bit different than derivative, a little bit different than the original function. Okay. For homework, try 1 through 25. 41, 43, 45. So 41 through 45. And you could try 59, which is really going to ask you to take a second derivative and show that a particular series satisfies that differential equation. Cool.